सर आपकी आवाज़ नहीं आ रही।
सॉरी बच्चों, ये तो आधा लेक्चर गुजर गया ऐसे। Again, look at this. We are discussing the covalent bond, simple molecular structure, and especially those molecules in which the central atom has ability to expand its octet, placing more than 8 electrons in its outer shell. Okay, and we are going to draw the dot and cross diagram for these molecules. Again, a covalent bond with the simple molecular structure. The first example was ICl3. So when iodine reacts with the chlorine, ICl3, right? So this is, you see, iodine uses 3 electrons to make a bond with the chlorine. So ICl3. Iodine has 7 electrons, so all 7 it can use. But out of the 7 electrons, it is using only 3 electrons, right? And this compound ICl formed. But as you can see, the valence shell of iodine now does not have only 6 electrons. It does have now 6, 7, 8, 9, 10 electrons. Okay. Similarly, the second example was second example, PCl5. PCl5. Phosphorus is in which group, bacho? Group 5. So phosphorus has 1, 2, 3, 4, 5 electrons. And the phosphorus outer shell is a third shell. So all 5 electrons the phosphorus can undergo with Cl to form what? PCl5. So now phosphorus has 10 electron in its valence shell, right? Or 5 pairs, you can see. And why the phosphorus can expand? Because the phosphorus outer shell is the third shell, and third shell has the capacity to place more than 8 electrons in the valence shell, right? Phosphorus, there is an element in the periodic table above the phosphorus, that is nitrogen. Nitrogen, although have 5 electrons in the outer shell, but it cannot use all the 5 electrons to make NCl5 because there are 8 electrons in the outer shell. Number 3, IF7. Again, iodine has 7 electrons in its valence shell, and in this case, you see it is using all the 7 electrons. Right, to make IF7. This is, you see, 14 electrons now in the valence shell of this IF7. Next, number 4 is, or in this case, the PCl5, you can draw the displayed formula like this. And in IF7, you can draw the formula like this. 1, 2, 3, 4, 5, 6, and 7. So IF7 is the 7 electron pairs around the central atom. Number 4, the next one, SO2, sulfur dioxide. Next one is sulfur dioxide. Sulfur dioxide. SO2. Sulfur dioxide, SO2. Now look at this. The central atom is sulfur having 1, 2, 3, 4, 5, 6 electrons. Right? Now look at this. It just needs 2 if you look at the octet. But sulfur's outer shell is not second shell. It's a third shell. So it can place more than 8 electrons. So one oxygen comes. It has to share 2 electrons. Another oxygen comes. It has to share 2 electrons. This becomes sulfur dioxide. Okay? So now sulfur dioxide has 1, 2, 3, 4, 5, 6, 7, 8. and 9, 10, 10 electrons. And the next one is sulfur trioxide. SO3. It has how many? 1, 2, 3, 4, 5, 6 electrons. So here it is. Right? So if you look at this is sulfur trioxide.
Then how can we define how much electron spectrum?
The maximum number of sulfur has 6, na? So obviously it can pair more than 6. So all 6 electrons it has to involve in the bonding to make 12 electrons. Iodine has 7 to make it 14, so something like this, right? Now, having said that, number 6 is PF5. You can do it yourself. I'm just leaving it here right now. The next one,
XCF4.
XCF4. Look at this, kids. This is xenon tetrafluoride. You know xenon is in group what? Group 8. So 1, 2, 3, 4, 5, 6, 7, 8 electrons. So if you just see the octet, so it's already completed. But again, xenon has the valence shell, which can accommodate more than 8 electrons, the third or fourth shell. So it's going to combine with 4 fluorines to make XCF4 like this. Okay, so the point has been made that the elements below the period 2 of the periodic table, they can use all their electrons, right, in the bonding and can place more than 8 electrons, known as octet expansion. Now, one thing which you have to be careful in this case, at time examiner asks you one thing, IF7 exists, but ICL7 does not exist. Why? That was the question. Okay, IF7 exists. In other words, iodine can make bonds with how many fluorine? 1, 2, 3, 4, 5, 6, 7. To make like this. But the same thing, when you look at the chlorine, they can maximum go ICl3. No, iodine, the central atom, it still has 7 electrons. 1, 2, 3, 4, 5, 6, 7. Why it can't use all 7 to make 14 with the chlorine? Now the difference, understand. Basically, I'll explain in the next part when we looking at the shapes of the molecule, but at this moment, I'll give you the information on need to know basis. These electron pairs which are present around the central atom of a molecule, you know, they repel each other. Both of them are what? Negatively charged. So what do? They repel each other. No, this is not spin. This is bond pair repulsion. They repel each other. Once they repel each other, so in case of fluorine, they are small atoms. But if you look at the chlorine, for example, they are bigger atoms. So once they repel each other, they actually covered so much area around the iodine that nothing is left. So if I show it like this, just for the sake of argument, so when 3 chlorines are here, one is on this side, one is on this side, one is on this side, so there is no space left. This is called steric hindrance. Okay, when these atoms, which are around the central atom of the molecule of the atom, they repel each other. They repel each other. This is, and because of this, they do not have enough space. And this phenomena is known as steric hindrance, right? So if the central atom has a big atoms around it, right? So because of steric hindrance, they can only, they cannot expand the octet. Otherwise, they can expand. So please write down, in case of ICl7, ICl7, oh sorry, yeah, in case of iodine, sorry, in case of iodine with chlorine, not ICl7, sorry, in case of iodine bonding with chlorine, there is more repulsion between the electrons of chlorine as chlorine has bigger atomic radius than fluorine. Phenomena known as steric hindrance. Steric hindrance. Hence, cannot form ICl7 unlike fluorine IF7. Here it is. So I hope you understand. I have given you the information on need to know basis. They ask you about the expansion of octet, but they rarely ask you about the steric hindrance, right? So I'm explaining it once again, just to make it short. Listen, everyone. I just said, okay, from here on, what we are going to think, okay, an atom, if it is not in the period 1 or the period 2 of the periodic table, okay, provided it is not in period 1 and period 2 of the periodic table, its outer electrons, all of them, 4, 5, 6, 7, they can involve in the covalent bonding. Like sulfur has 6, so it can pair with 6 more electrons, right? And total electrons, how many will be there? 6 times 2 is what? 12 electrons, just like SF6. Okay? Because sulfur's outer shell is third shell, having 12 electrons, can accommodate 12 electrons because the total capacity is more than 12. Why the period 2 elements? Just above this is oxygen. Why OF6 not possible? Because the oxygen's valence shell is in period 2, so the valence shell is second shell, which has the capacity of only 8 electrons, so it can maximum form OF2. It cannot form more than that, because that completes the 8 electron in the outer shell, and as that also fills its octet and as well as its capacity, right? Because oxygen's capacity for the second shell is this. You got it? Now, next question which the examiner they may ask, कि क्या every atom which is below the period 2 can expand its octet without any factor? We say no. We have to see that the central atom of the molecule must have enough space around it to accommodate the atoms. For example, you see around the iodine, we placed how many fluorines? 7. But when we placed chlorine around the iodine, it was not possible to place 7 chlorine, because these chlorines have their valence electrons which are repelling each other, right? And the chlorine size is bigger. Down the group atomic radius increases. So therefore, the repulsion between the chlorine, this is called, this repulsion, I'm naming it as steric hindrance. So because of steric hindrance, there is not enough space available around the iodine. So that's why the iodine cannot make with the chlorine ICl7. On the other hand, it can. So what I'm saying, that iodine being 7 electrons in the valence shell can accommodate as much as electrons possible until there is no steric hindrance, right? When the steric hindrance comes in, then they stop it. Otherwise, it uses all its 7 electrons to make 14 electrons in the outermost shell, right? So that's all about this covalent bond, dot and cross diagrams with a simple molecular structure, right? That's all about this topic. Now we'll continue with the next in the same thing, that is the shapes of the covalent molecules. So please give a heading. No, not sorry. We'll continue with this, the coordinate bond or dative covalent bond. Before we shapes, we have not finished the covalent bond. Okay, please pay attention. Now, the same thing, the octet expansion we just explained, there are some dot and cross diagram in the covalent compounds which needs more explanation. For example, let me explain this. There is a molecule that is known as ammonium. The formula is NH4 positive. If we look at the ammonium ion, there is a nitrogen having 1, 2, 3, 4, 5 electrons in the valence shell. It combines with 3 hydrogens to make a covalent bond like this, NH3. Okay, this is NH3, ammonia. Now, if you look at the nitrogen, how many nitrogen has electrons in its valence shell? 5. Now, after combining with 3 hydrogen, how many electrons? 8. But still nitrogen has 2 electrons available, free. जिन्हें हम क्या बोलते हैं? We call them lone pair. So nitrogen wants to use these electrons in the process of bonding, but unfortunately it cannot. Ideally, it should make with 2 more hydrogens like this to use all its electron, expand its octet, but it's not possible for the nitrogen. Why it's not possible for the nitrogen? Because nitrogen is period 2 and its outer shell has how many capacity? 8. So it cannot expand its octet. So even if it has to bond with another hydrogen, it has to find another way. And what is that way? Look at this. It actually combines with H positive ion. Now, if you look at the H positive ion, hydrogen, we all know, has 1 proton and 1 electron in its outer shell. But when it becomes H positive, that electron is lost. So what is left? Only 1 proton. So this hydrogen now can accept 2 electrons in its outer shell. Is it so? Because first shell is the outer shell and it's completely empty. Right? So what they do, the nitrogen now bonds with not hydrogen, with H positive. Right? Using its lone pair, this one. Can it transfer? No. Can it share mutually? No. But what they do, they share the electron pair, but this electron pair which is shared belongs to nitrogen only. This is the bond which is formed between them, and this is known as dative covalent bond. It's just like, let me explain. It's simply like this. The bond down. What I'm trying to say that the bond which is formed by the sharing electron is known as covalent bond. But if the shared pair is equally divided like this, it's a simple covalent bond. But if the shared pair is like this, the both electrons belong to one atom, it is known as dative covalent bond. And let me tell you, once it is formed, it behaves like a normal covalent bond. Its length, its strength, its width, its energy, everything is just like a covalent bond. So I hope you understand what I'm trying to say. If atoms find another way to share the electrons, so instead of mutually sharing, they can share a pair which belongs to one atom, that is also known as covalent bond. And once it is formed, it behaves like a normal covalent bond. For example, in ammonium, if I say this bond, and this bond is what? Covalent bond, but the one which is on the top with H positive, it is what? Dative bond. In order to just distinguish, I'm putting an arrow from donor to acceptor. But that does not mean that bond has a different length, different strength, different energy, nothing. They all are this one, this one, this one, and this one. They all are what? They all are the same. They all are the same. So this is what I'm trying to say, that from here onward, what we are going to think, the bond which is formed by the sharing of electron is the covalent bond. If one atom is giving both electrons, the full pair, that will be a dative covalent bond. If the one electron comes from one atom and the other from the other side, it will be a covalent. But once they are formed, they behave like a normal covalent bond. Everything is the same, right? So if somebody asks me to break the ammonium bonds, the 4 bonds in the ammonium, do I need some different kind of energy to break the one on the top? I mean the dative bond? No, absolutely not. Right? So it's very slight difference. It's a very, very slight difference, right? So please write it down just to make you understand. Definition: the bond formed by sharing of electrons, but the electron pair shared belongs to one atom only. Put a star and write down. Once it is formed, it behaves like a normal covalent bond. But in order to distinguish, we just put an arrow like this. Unlike a straight line, we put an arrow from donor to acceptor. And we have to look at few examples, not all of them, few examples, which are having this type of bond. And one of them is ammonium ion. So what I'm trying, that from here on, you don't think that dative covalent bond is a different bond. It is a covalent bond. Coordinate or dative covalent bond is not a different, it is a covalent bond, just a type of covalent bond in which 2 atoms share the electron, but the electron pair that is shared is given by one atom only, right? And there is no other difference, right? Once we'll do the organic chemistry, the next section which we are going to do, you will see and understand every bond that is going to be formed is always a dative. First time when they come, they may not be sharing the equal or mutual electrons. They always come with an electron pair, bond it, and then later on they can share their electrons equally. Okay? Okay, one is ammonium ion. Please draw this diagram for the ammonium ion. Please draw this diagram as an example of ammonium. So I'll give you 3 or 4 examples. So again, I hope you're understanding. We're just justifying the dot and cross diagram. The examiners are not interested that you know the covalent bond ki ek aur type hai. It's not that. They just ask you to justify the dot and cross diagrams. Okay, how water formed H2O, how PCl5 formed, how IF7 formed, how NH4 positive formed. So you just have to justify okay, how these dot and cross diagrams, how the bonding takes place in these, right? So in this particular case, we justified that the 3 bonds are mutual sharing and one of them is again sharing, but the shared pair is given by one atom only, right? Usually the atoms which have the lone pair of electrons that they cannot expand their octets, they would like to make this type of bond, okay? Otherwise, if they have an option to expand their octets, they would go for the normal sharing, okay? Now look at this, number 2, oxonium ion. Just put a bracket around ammonium ion. Number 2 is oxonium ion. H3O positive. I'm giving you 2 minutes. Please try to first make water, the dot and cross diagram for the water, and then look for the H positive ion. Oxygen has how many electrons in the valence shell? 6. If it makes a covalent bond with one hydrogen, covalent bond with another hydrogen, and there is an H positive. Obviously, H positive has nothing to share. So if H positive and water is going to make bond, the electron pair that is going to be shared will be given by oxygen only. But as I said, this is not something very special. It's a simple, normal thing. The thing which you need to understand that the covalent bond is the bond that is formed by the sharing of electron, right? So this electron pair is now shared between these two. And once it is formed, this oxygen, and this H positive.
So we need to show that positive.
Yeah.
In the diagram. Okay.
Next, one more example, carbon monoxide. This is another molecule which needs a dative covalent bond to justify the bonding. Carbon monoxide. Carbon has 1, 2, 3, 4. It shares electron with one oxygen. Now what next? Oxygen has complete octet. What about the carbon? Carbon has 6. And both of them cannot expand their octets. If carbon could have expanded its octet, so that will be another situation. But now, what is the situation? They have only one oxygen, there's one carbon. What they're going to do? Oxygen offers this electron pair to be shared again. Now, this shared pair is here now. Now, if you look at this, it goes like this. You see? What is this? Dative covalent bond. But once, as I said before, once it is formed, it behaves like normal covalent bond. So, इसीलिए they tell you that the carbon oxygen has a triple covalent bond. Usually they don't say. Precisely the carbon oxygen in carbon monoxide has triple covalent bond because all three bonds have the same length, strength, energy, everything. But we know that two of them are formed by the sharing with equal number from the both sides, and one of them formed by the sharing. So all three of them formed by the sharing of electrons. Number 4. Next is
Al2O6.
yeah. The next is first let me tell you aluminum chloride. Aluminum chloride. Yes, this is AlCl3 but it has a unique feature in which when you take the molecules of AlCl3 in a beaker, they start pairing up together. The pairing, okay? Like water, if you look at the water molecule, there is one molecule, there's another, there's another, there is another. They don't pair up. But there are some molecules in the universe in which they exist as a simple molecular, but two of them are paired like this. Yes. Aluminum chloride has this feature. Okay, in its beaker, when you take the aluminum chloride, they turn into Al2Cl6. What does it mean? Okay, one molecule of aluminum chloride combines with another molecule. This pairing phenomena, known as dimerization, can happen in a lot of molecules. Right? Now we are going to see what is this force. Dimerization is not the part of our syllabus to discuss. I just told you what is this phenomena actually. But in our syllabus, we are supposed to discuss what is the force that dimerizes them. In aluminum chloride, the force is like this. This is aluminum. Look. AlCl3, molecule number 1 I'm assigning. This is another molecule of aluminum. I'm saying it's molecule number 2.
Is a container?
In a one container, the two molecules living together, just like water. If I have this water molecule living together, but they are not paired up. Every single molecule of water is independently living. Here, what I'm going to tell you, that two molecules of AlCl3, here it is one AlCl3, and here it is what? Another AlCl. They are going to pair up. Why they pair up and how they pair up? That's the question here. If you look at the aluminum chloride, how many electrons aluminum has in the valence shell? Does it has two more electrons ability to accept? Same is the case with this. Number 2 molecules aluminum chloride. So what happens? The number 1 molecule of aluminum chloride, now listen carefully. Its chlorine uses its one of the lone pair to share with the aluminum of number 2, not number 1, number 2. Now I'm going to take this electron pair off and put it here. So now the bond is formed between them. And again, this bond is what? Covalent. But the shared pair of electron belongs to what? Shared pair of electron belongs to? Cl. And now precisely saying there will be absolutely no difference between these two bonds. Here the same chlorine is making covalent bond and the other side it is making what? Dative covalent. But the bond which is formed, sharing of electron, it behaves the same. Now as a result of this, the aluminum chloride number 2 molecule has now complete octet. But look at the AlCl3 of molecule number 1. Still needs 2 more. So number 2 का जो molecule है, उसका जो chlorine है, it will reciprocate. Will give its one electron pair to this. Here. Do you get it? So again, look, what I said, let's see. We are going back. Here. This is the status. Now, AlCl3 number 1, AlCl3 number. You recognize that? The number 2 molecules, aluminum has how many electrons? 6. How many it needs more? So one of the Cl from the number 1 is going to share its electron pair with that chlorine. There is no issue. They can share, in which the electron pair given by the chlorine only. Look. Here. Now, that's aluminum has complete octet. And in order to reciprocate this action from the molecule number 1, the molecule number 2's chlorine, which is down there, it's going to make a dative bond with the aluminum of the first one. Look. Here it is. You see? Now this lone pair of electron that is present with the chlorine is going to be used, the one which is just erased, between, you see? Okay, now I would like to write like this. Look, this is aluminum, parents, one chlorine, one chlorine, one chlorine, right? This is, look at this, Al, Cl, Cl, and then Cl, right? Now, this chlorine, dative bond with this, and this chlorine made a dative bond with this. This is what how you have. Okay?
And so this will keep on going on.
Yes. Now this is the molecule number 1 and 2 are joined like this. Similarly, if the beaker is, let's say, big enough, and this process continues. Here is 1 and 2 joined. Here will be 3 and 4 joined. Okay? And then 5 and 6 joined. But the force of joining is what? Dative covalent bond, right? Same is the case if I take ALI3, it turns into what? ALI6. Can you please draw it now with me? You will lead ALI3 turning into ALI6. So yeah, Al2I6. Aluminum is again in which here 3 electrons. Iodine shares 1 electron here, 1 here, 1. This is ALI3, 1 molecule. This is ALI3, another molecule. First, you draw both ALI3 separately. Okay? Now, what next?
The iodines.
This is molecule number 1, this is molecule number 2. So, one's iodine. Yes. As the lone pairs, 3 of them, will use 1 of them to make a covalent bond with the aluminum of number 2. So, this one, they are going to use. Okay? So, I'm going to remove it from here. On the other hand, the number 2's iodine, one of the iodine uses this lone pair to make, yes, with the aluminum 1. Okay? So, here it is. Right? So, this is ALI. But as I said and repeat myself, once they are formed, they behave like here. So look at this. Here and then here. Okay, this is Al2, I6. Right? So these are the few examples. So let me wind up now this. That we discussed the dative, we discussed the covalent bond, simple molecular structure, how the tiny number of atoms combine to make tiny molecules. And we justified their dot and cross by using additional 2 things, expansion of octet and the dative covalent bond, which we were previously not using in O-levels, right? So that's all about this. Tomorrow we're going to see the shapes of these molecules. Thank you very much. That's all.